Okay, now let us understand it little more further. Okay, I want to make this problem more simple, so I consider pure rotation without translation. Means I'm not considering translation for these calculations. What I'm going to do is I'm going to understand the change in quantities with the time. Okay, I'm going to understand time change with the uh, position vector, velocity, etc. Okay, for understanding further, let us understand the coordinate system well. So I have an inertial coordinate system x, y, z as you have seen, and I have a rotating coordinate system x prime, y prime, z prime, and it rotates about its z prime axis. Okay, with an angular velocity omega. So omega is the angular velocity which rotates about the z axis, or omega can be represented as omega is equal to omega into k. K is the unit vector along the z direction, right? So I use the red color for the rotating frame and the black color for the inertial system, right? So we have two systems, inertial and rotating systems. Okay, and now let us assume the origin of both the coordinates coincides. So it will look like this. The x, y, z axis represents the inertial system, x prime, y prime, z prime represent the rotating system. Okay, see, in this case x varies. So what happened? There is a difference. So you know I is the unit vector along the x direction, j is the unit vector along the y direction, and k is the unit vector along the z direction. But both the cases z and z prime are in the same direction. There is no change for k and k prime. But see here in x prime, the direction of unit vector changes. Okay, so when you calculating the differential, you want to calculate change in unit vector also. That is, you want to calculate d by dt of unit vector I, and d by dt of unit vector j, and d by dt of unit vector k, like that. Okay, what I mean. So this is what system when they have a unique origin, or they coincide. Okay, now I'm considering at any time. So the second coordinate is rotating, the rotating frame is rotating at any time t. The coordinate will coincide, means x, like this, x will coincide with x prime, y coincide with y prime, and z is coincide with z prime always, because it is rotating along this axis. So I am measuring a position vector of any particle r of t. Okay, so r of t is the position vector in the x z plane for the inertial system, and for the rotating frame it is the x prime z prime coordinate at time t, right? Okay, now I am calculating these things in a later time. So later time means time t plus delta t. Delta t is the variation, a small variation. So let us calculate this in the first inertial coordinate. The inertial coordinate, so r of t is the position vector in the xz plane. After some time it reaches here, okay, some position. So the position vector is r of t plus delta t, and the difference is delta r. That is the displacement. Okay, this difference is the displacement. Therefore the displacement you can calculate from the vectors. Here r of t plus delta r is equal to r of t plus delta t. Therefore displacement delta r is equal to r of t plus delta t minus r of t. It's very clear. Okay, now the same we can calculate for the rotating frame, right? So the rotating frame, he also sees the same end point. Okay, he also sees the same end point, but he remember the initial point or the initial position vector at time t that he was measured in the x prime z prime plane. Okay, I will repeat once again. He will see the same endpoint as like in the inertial frame, but he remember, because he sees the endpoint, then he think about the initial point. He remember that the initial point that he measured was in the x prime z prime plane, not in xz plane. Okay, so in the x prime z prime plane, he will remember it is r prime of t. So this is r prime of t. So therefore the construction r prime of t, this is r prime of t plus delta t, but this is same as r of t plus delta t, and delta r prime is the displacement in the rotating frame. Okay, what we want to know is the displacement in the inertial frame and the displacement in the non-inertial frame will be same. That is our first interest. Okay, so let us calculate. Here delta r prime can be calculated from the vector construction. So therefore delta r prime is r of t plus delta t minus r prime of t. Okay, so in order to understand the difference in delta r and delta r prime, I combine the two situations, means the inertial and the rotative frame. That will be like this. See, here the red one is a rotating one and the black one is the inertial one. Okay, you have seen everything. So but there is a green one. The green one is this thing that is actually constructed from these vectors r of t and r prime of t. Therefore this green vector is r prime of t minus r of t. Okay, so we want to know the relation between delta r and delta r prime. We can construct it from this triangle. Okay, from the vector constructions. From that, r prime of t minus r of t plus delta r prime is equal to delta r, or delta r is equal to delta r prime plus r prime of t minus r of t. Therefore delta r and delta r prime are not same in a rotating frame. It is only due to r prime of t minus r of t, but r prime of t minus r of t arises due to rotation. Suppose there was no rotation, r prime of t will be equal to r of t and delta r will be delta r prime. Is it clear? Okay, so what we can say is, another way, the velocities is different in the two frames since the displacements are different, right? Let us do little more. So once again I repeat, r prime of t and r of t differ only due to pure rotation, and from our earlier understanding we know dr by dt is velocity, that is equal to omega cross r, where omega is the angular velocity that you have learned in the last semester. If you want to clear more, you refer chapter 7 in the textbook. Okay, so using that, r prime of t minus r of t is omega cross r into delta t. So we have delta r is equal to delta r prime plus delta r prime of t minus r of t. I am dividing both sides with the delta t, so therefore delta r by delta t is delta r prime by delta t plus r prime of t minus r of t by delta t. Utilizing your earlier understanding, delta r by delta t is equal to delta r prime by delta t plus omega cross r. Here I am using the capital omega. That's all. It's again the angular velocity. Now taking the limit delta t tending to 0 for a small difference. Suppose the time difference is very small. Okay, delta t tending to 0, but actually it is delta t tending to 0 means limit delta t tending to 0, delta r by delta t is actually dr by dt, but it is the velocity, as it's instantaneous velocity that we know. Okay, so limiting, we are getting delta r by delta t limit delta t tending to delta r by delta t, that is actually the velocity in the inertial frame. Similarly, v rotation is the velocity in the rotating frame, that is the limit delta t tending 0 delta r prime by delta t plus omega cross r. Very important relation. V inertial is equal to v rotational plus omega cross r. The change in v inertial and v rotational is due to omega. Omega is actually the angular velocity. This can be written in another form, dr by dt inertial is equal to dr by dt rotational plus omega cross r. This is just another notation, way of writing. Okay, but r is not a general one. We can calculate the same thing for any general case. For example, a general vector b. So in the case of general vector b, it will look like this. This vector construction look like this: b of t, b prime of t, delta b prime, delta b, everything is there. So the relation will be d by dt of b in inertial is equal to d by dt of b in rotational plus omega cross b. So this can be utilized for our further calculations. Okay.